In this video, we're going to discuss how to evaluate scientific claims and how to understand primary literature. We have a quote here by the American futurist and a former editor of Fortune magazine, Alvin Toffler. And what he said was that the illiterate of the 21st century will not be those who cannot read and write, but those who cannot learn, unlearn, and relearn. And this is so true. What he means here is that, of course, people in the 21st century should be able to read and should be able to write. But the difference is this, is that we are being absolutely bombarded with information every day, coming through on your Facebook feeds, coming through on Twitter, just constantly at the tip of your fingers at a Google search. You have a massive amount of information at your disposal. The problem is not all information is credible. And so the difference between what will make a good citizen and a poor citizen, or a well-informed citizen and a poorly informed citizen, is these new abilities. These ability to not only learn, but to unlearn and relearn. Okay? To be able to sift through this information, to sift through this data and determine, that is a good source of data, let's take that in. Oh, wait a minute, here's a new source of data that conflicts with what I had before. Okay, I'll have to unlearn that and relearn that. Let me give you an example in my own life of what he means here by learn, unlearn, relearn. When COVID first started, when it was still primarily in China, people would come up to me because they knew I had a PhD in biology, and they say, oh, hey, what do you think about this COVID? Oh, should we start wearing masks and stuff? And at that time, early on, it was known that COVID, of course, was caused by this virus, and viruses are very, very small, slip through the cracks of a mask. And so based on that data, I thought, no, and the consensus was, oh, masks aren't going to do any good. We're talking about a virus can slip through those masks, definitely of the ones that you would buy in a store or make on your own. But then, as the months went by, as more and more data was collected, there came out studies that used rigorous scientific methods to study the effect of masks on preventing people from either transmitting or coming down with COVID. And sure enough, from this data, they found that masks, even your homemade masks made out of cloth, are in some ways effective at keeping the virus out. Obviously not 100% effective, but that's not the point. The point is it is better than not having a mask. And so when I came to that data, I looked at it, I looked at the science behind it, I listened to the experts, and I now start wearing masks. So I have learned, I have then looked at the data, I have unlearned, and then I've relearned based on new sources of credible data. In this lecture, we're going to be talking specifically about scientific claims. And so we need to define what a scientific claim is. And to best understand what a scientific claim is, let's talk about what it's not. It has nothing to do with opinion. You don't have an opinion on a scientific claim. So the Mona Lisa is a beautiful painting is not a scientific claim. You can't really provide data that proves objectively that the Mona Lisa is a beautiful painting. It's a matter of opinion. Some people think it is. Some people think it's not. You can't provide data. You can't come up with a test or an experiment that supports objectively that baseball is a boring sport. Some people think it's exciting. Some people think it's boring. You can have an opinion on whether or not baseball is boring. So those are not scientific claims. They are opinions. Scientific claims, on the other hand, are testable. You can provide data that will either support or refute that particular scientific claim. So for example, if I say my TV won't turn on because the batteries in the remote are dead, that is a scientific claim that can be backed up by data, that can be backed up by a test. And notice, this is just a simple sentence. The claim that you make does not have to sound science-y to be a scientific claim. My TV won't turn on because the batteries in the remote are dead is a scientific claim without sounding science-y. Now, how would I test this claim? Well, I'd pull out the batteries, I'd put in a new pair of batteries, and if it works, lo and behold, I've just produced data that supports the idea, that supports the scientific claim that my TV won't turn on because the batteries in the remote are dead. So scientific claims are testable. You can produce data that will either refute or support the scientific claim. Now, scientific claims aren't necessarily true, right? It's possible somebody will put forth a scientific claim that will later have data that refutes it, okay? And just because somebody on the internet says it doesn't mean it's true. Just because it sounds science-y and rational and logical doesn't make it true. If you hear this scientific claim, you're going to want to look for data that either supports or refutes it. So for example, here we have Kangen water. Some of you may have heard of Kangen water. These are the alkali water. And I've looked on the internet and I found that, oh, look at that. They are free radical scavenging. Ionized alkaline water supports the wellness of bodily organs while promoting the health of those same organs. Part of the reason for these benefits is that ionized alkaline water has been demonstrated to be an antioxidant free radical scavenger. Well, that is a scientific claim. That sounds pretty darn science-y, pretty darn rational and logical, but there's no data to support that. And in fact, they said it's been demonstrated, but they don't provide, right? They don't provide a link or anything to the data that supposedly supports this. So just because something sounds science-y and rational and logical doesn't necessarily mean it's true. Look for the source of the data. Okay, see if that data supports it, or see if you have to reject that scientific claim. Okay, so we hear a scientific claim, or we read about a particular scientific claim. Let's evaluate it. What are good and poor sources of scientific claims? Well, when we start evaluating these claims, we have to check for bias or agenda. Does the person making the claim gain something if others accept it? Well, if you are reading a particular scientific claim in an advertisement, well, of course they've got this motive of making money, of getting you to buy it, right? These barefoot running things from Vibrant, they got into a lot of trouble. They made all kinds of scientific claims that were proved to be not true, and they got in trouble for that. Okay? Lots of beauty products have all kinds of scientific claims. Even on something as simple as cereal can help lower cholesterol and reduce the risk of heart disease. And see that little asterisk there? If you take a look and read a little bit more, this is a pretty good example of a scientific claim on an advertisement that actually has science to back it up. You can look at that asterisk, and on the back of the box they will explain what they mean here. Okay, so not all advertisers are making false scientific claims, but it's worth knowing that, hey, these are advertisements. They have an ulterior motive here, which is to get your money. So you better take a closer look at those claims and look at data that maybe supports or rejects those claims beyond just the face value of reading it off the box. Special interest groups, like religious groups or political groups, right? They gain supporters. Okay, so make sure if you see a scientific claim coming out of a political group or a religious group that, again, you seek out other sources of data that may support or reject those claims. And hopefully, if they are doing things well, when the political group or when the religious group spouts or says a particular scientific claim, that they themselves point you out to data that supports, credible data that supports or rejects that scientific claim. Look at the author. Look at the person who is making that particular claim. What is that author's credentials? Do they have the education necessary to understand the claim that they are making? Do they have an MD? Do they have a PhD? Do they have some higher level degree in a relevant field? So for example, if we have this scientific claim, a new herbal supplement called Placebex will make you thin in 1 week. If we hear this from celebrities, like Jenny McCarthy or Gwyneth Paltrow, is a celebrity a credible source of this information? I'm pretty sure neither of these people have advanced degrees in chemistry or medicine, right? She's obviously involved in the anti-vax movement, and she has a company that has all kinds of pseudoscience products. Okay, so then there are people that do have advanced degrees, and yet we should be careful. So the Dr. Oz show here, Dr. Oz actually has a MD. He's actually evidently a respected surgeon. However, he has a TV show, and he has advertisers that pay him money to advertise various supplements. And so we should be a little cautious. Okay, we should look at alternative sources of information about whatever claims he happens to be making or advertising. And this one is one that has become an epidemic in the US. Is your intuition, is your gut feeling a good source of scientific information, of judging scientific claims? Oh, I think the earth is flat. I think that vaccines are not very good. Right? We're assuming we're talking about people who don't have the expertise to judge this. And again, I think many of you would understand and have seen this in the US, definitely, within the last 6 months, let alone the last 10 years. Even Isaac Asimov back in the 80s was quoted as saying, there is a cult of ignorance in the United States, and there always has been. The strain of anti-intellectualism has been a constant thread winding its way through our political and cultural life, nurtured by the false notion that democracy means that my ignorance is just as good as your knowledge. Meaning, I have the right. This is democracy. I can say that masks don't work. You have to respect that. Right? Instead of taking the advice of people who have advanced degrees in epidemiology and science and who are cautioning us, please wear masks. So, unless you have an advanced degree in the particular subject you are looking at, then your gut feeling, your intuition is not a good source to judge a scientific claim. Okay? Let experts be experts and look at the data they present. So, with that said, what is the most credible source of information regarding any scientific claim? And I looked on the internet and I found another really good quote. Martin Luther King Jr. said it best when he said that not everything you read on the internet is true. And this is so true. So what is the ultimate source of credible information about a scientific claim? Science, scientific studies, right? The scientific method, an organized and logical way of testing a scientific claim. In other words, we're testing a hypothesis. That scientific claim in science speak is called a hypothesis. And it is through these scientific papers or journal articles or primary research papers that the data that either refutes or backs up or supports a particular scientific claim, that's where they're published. That's where we'll see them. And why is it that they're so credible? How do they get published? How do we find them? And this is the process here by which primary scientific literature is published. This is the process of science itself, of why science is the best source of information that we have so far. And this is the way it works. We have labs and scientists in those labs, like Shinya Yamanaka in Kyoto University, and they have questions they want to answer. He wants to know, can specialized cells be reprogrammed into embryonic stem cells? So embryonic stem cells are very nice. They can be turned into any type of cell, but the problem is to get them, you need to sacrifice an embryo, and that causes all sorts of issues, ethical issues and such. So if we could take specialized cells like your skin cells and turn them into something like embryonic stem cells, that would be pretty awesome. And so that's what he was trying to research. So he did some research, and he found that when you force these specialized cells to express 4 important genes, it reprograms the cells into embryonic stem cells. Aha! He found a way to do this, and he provided data that supports the ability to do this. So he and his colleagues wrote a manuscript, wrote up a primary research journal article going through all of the data that they came up with that supports this hypothesis that he can reprogram cells into embryonic stem cells. But that's not enough. Right? That's not enough. He first then submits that to a journal. There's all sorts of scientific journals out there. This one is Cell, there's Nature, there's Science, and the different journals have different impact factors. And what an impact factor is basically how many people really want to read it. If the journal has a really high impact factor, that means lots and lots of scientists want to get their stuff into that journal because lots and lots of people read it. Now, that journal, the editors of that journal, they look at that manuscript and they say, hey, we don't have the scientific expertise to critically evaluate this science that's in this manuscript here. We want to make sure it was good science. We want to make sure there were good controls. We want to make sure the experiments worked properly. We want to make sure that the conclusions were backed up by the data. But we don't have the expertise to figure that out. So what they do, and here's the super important part of science, is they take that manuscript before publishing it, and they send it to other scientists who study similar things as Dr. Yamanaka here. Scientists who have the academic knowledge and education to be able to look at the science in this manuscript and be able to critically evaluate it. And because they are colleagues of Yamanaka, because they are, we call that peer review. So this manuscript is being reviewed by Shinya Yamanaka's peers, people who have that same education as him, same interests as him. Now, those peers, they'll read that manuscript, they'll critically evaluate that manuscript, and they'll send back reports to the journal, and they'll say, yes, this is good stuff. Please, you should definitely publish this. They'll recommend to the journal, accept. Or sometimes they'll say, all right, well, it's good, but he needs to do this experiment, they need to do this experiment, and then it'll be really good. And so they would then recommend to revise the manuscript, to do some more experiments. And so the journal will send the manuscript back to Dr. Yamanaka. He'll do some extra experiments. He'll modify that manuscript, send it back, and then the journal will publish it. And finally, the last possibility and the worst possibility is that the peer reviewers will recommend that the journal reject it. Now, there's a couple different reasons why they might suggest that the journal rejects it. The most likely reason is this. As I said, different journals have different impact factors. And the really high impact factor journals like Cell, like Nature, like Science can be very selective. They can basically reject a paper not because it's no good, but because it's not exciting. And so they only accept the papers that are going to make huge headlines or tend to make big headlines. So oftentimes the peer reviewers will say, hey, this is good stuff, but it's really not exciting. It's really not a paper that should be published in Cell, and they'll reject it that way. And then the author would take that manuscript and then just take it to another more lower impact journal and get it published there. The alternative is the peer review say, you should reject this because this paper is no good. That science that's been done is a little sketchy. The controls aren't working the way they should be working. Do not publish it. Right? And so that is the process by which papers are reviewed, rejected, or published. Let's assume, well, because if we are talking about Shinya Yamanaka here, his paper about this stuff did get published. And it got published in the journal. So basically, if you were to get a physical version of the journal, you would have a whole bunch of scientific articles in that one journal that you would get for that month. Nowadays, oftentimes this is all available online. And so if you were to look at the first page of this particular article, you'd have the title, Induction of Pluripotent Stem Cells from Adult Human Fibroblasts by Defined Factors. You've got the authors, you got the institutions where that research was being done, the abstract, or sometimes called the summary, and then the rest of that paper. Now, I didn't choose this particular paper or this particular author randomly. Turns out this is super exciting research, so much so that Dr. Yamanaka won the Nobel Prize for this research just several years ago. So it's a really big deal. Now, it is still possible for mistakes to have been published, for fraud to have gotten through. But fortunately, science is or tends to be self-correcting. When other researchers look at published experiments, they often want to build upon them. And to build upon them, they have to sort of repeat those experiments, get them working in their own labs, and then start building upon it. Well, what happens is when a bunch of researchers see a published paper and say, hey, this will work really well in my lab, then I can do this and this and this. They try to repeat it and they go, wait, hey, I couldn't get that to go. And then another lab might say, hey, we couldn't get it to go either. Well, everybody starts doing that. They start going to the original researcher and they start asking questions. And sure enough, it's possible. And there has been fraud. For example, there was a paper a little while ago that was talking about stimulus-triggered acquisition of pluripotency. So it's basically very similar, but an easier process than what Dr. Yamanaka was proposing. Okay, that would have been revolutionary if you had this easier process to do these, to make these type of cells that Dr. Yamanaka was. Well, it turned out that there was faked data in those experiments, and it was fraudulent. Okay. There's also negligence as well. There's some researchers who will themselves go back and say, whoa, hold up, we made some mistakes. This paper has to be retracted. My bad. We're no good. So that happens as well. The paper, there was negligence, right? And the papers that we're talking about, one paper that talks about vaccine causing autism, there were all sorts of problems later on found with that paper. There was conflicts of interest and self-selecting groups, and it caused all kinds of problems. And indeed, the author of that paper lost his MD license. So science is, for the most part, self-correcting. So between this process of peer review, it is the best source of information we have on data that will either refute or support scientific claims. So in summary then, scientific claims do not involve opinion. That's something different. Scientific claims can be supported or refuted by tests that produce data. That when we're looking at a scientific claim, we want to be aware of the source of that claim. Okay? We want to look for data independently of the person who made that claim. We want to look for data that either supports or refutes that claim. Incredible data. We want to learn about peer-reviewed primary scientific articles and know that they are the best source of data for scientific claims.